All right, guys. So chapter 10, temperature and heat. This chapter is gonna show you a few properties that we go over in physics in regards to temperature, heat, thermal energy, latent heat, specific heat capacity, and a little bit of the laws of thermodynamics. Okay. Again, focus on the concepts. All right, focus on the definitions like what's temperature, temperature scales, heat, latent heat, what's latent heat. And then let's start with temperature, which is basically a measurement of the average kinetic energy of molecules. All right. Temperature is not exactly heat, although they are closely related, right? Temperature has to go, is a measurement on how fast molecules are moving in a mass. And we can use different scales for temperature, right? The most common one is the thermometer, which, as you know, uses mercury that expands due to temperature differences, right? This is something that we commonly know in physics as dilation of materials. When a material dilates, it expands. Now, using this thermal expansion, we can see how much the mercury has expanded inside a tube. Now, this has to do with thermal contact and equilibrium. You see, if you're trying to measure the temperature of a body, you're going to use a thermometer, but you are basically finding the thermal equilibrium between the two objects, which is given here. And that's the zero law of thermodynamics, by the way. When two or more objects reach what we know as thermal equilibrium. Think in terms of when you're trying to cool down a cup of coffee, and let's say you throw some ice in there, right? Or if you have hot water, or if you have cold water and you put some hot water, both are going to, well, one is going to gain heat, the other one is going to lose it. And eventually they reach the equilibrium temperature, which is what we know as thermal equilibrium. Okay. Now, in terms of the scales, the one that we use in the US is the Fahrenheit, right? So we know that the freezing temperature of water is 32, the boiling temperature of water is 212 Fahrenheit. In Celsius, which is the one that we mostly use around the world, it goes from 0 to 100. From 0 degrees Celsius, the freezing temperature of water, to 100 degrees Celsius, the boiling temperature of water. Okay? Why is that? Because if you think about it, it's easier. It's kind of like using a ruler with 100 divisions. Instead of 100 centimeters, you have 100 degrees. Okay? Now, when we want to analyze, when we want to introduce the idea of the absolute zero, right, which is not the 0 Celsius or 0 Fahrenheit. The absolute zero is a value where every molecular motion or atomic motion stops. And that's actually something that is not easy to achieve, right? We have extreme situations where, like, you can lower the temperature close to the absolute zero, right? Not necessarily in experimental physics, but we know of exotic matter that can reach values that are very, very close to the absolute zero, but we haven't reached that value yet, right? And the reason is simple, because we basically have a mass without any sort of atomic motion, right? And now, how do we find the absolute zero? By using the line function of pressure and temperature, right? As you see in that graph. And we see that the absolute zero is reached when the temperature scale reaches negative 273.2 Celsius, right? That is the temperature of the absolute zero, which we know as 0 Kelvin. You see, in science, the temperature that we use the most, the temperature scale that we use the most, is Kelvin. right? If we want to analyze or we want to write down the surface temperature of a star, the temperature of a core of a star or a planet, we write it in kelvins. For example, the temperature of the core of the sun is 10 million kelvins, and the surface is about 5,800 Kelvin. Now, for very large values of temperatures, guys, because of that relationship that you see there between kelvins and Celsius, if you're looking at millions of kelvins, you are also effectively looking at millions of Celsius. Okay? There's not really much of a difference. It makes more sense to look at the difference when you're looking at small values of temperature in both Celsius and Kelvins. Okay? Can anything get colder than zero? No, that's the absolute zero. Can the absolute zero ever be reached? No. Okay, so it's an extreme value like an asymptote, right, that we cannot really reach. But it still is worth analyzing and studying. Now, what about heat and a specific heat capacity? You see, when we talk about heat, you have to think in terms of thermal energy and transfer of energy from a hot body to a cold body. If you have ice and you place it on the stove is going to start melting the ice because it's transferring heat from the stove to the ice. That's basically what it is. Okay? So that's how we use the term heat. So heat is a form of energy, not a temperature scale. However, we're going to learn now how heat depends on temperature. First of all, one of the main factors for heat is a specific heat capacity, which is the amount of energy needed by a substance to increase its temperature by 1 degree Celsius. Right? For example, for water, the specific heat capacity is 4,186 joules per kilogram per Celsius. What does that mean? That means that you need that amount of energy, 4,186 joules, to increase by 1 Celsius. Now, that is about 1,000 calories, which we know as 1 kilocalorie. Okay? 1 calorie is about 4.18 joules. Okay? And then that's how you know why we use calories when, for example, we are in the gym and you are burning calories by doing exercise. You are releasing energy as you do exercise. That energy can be quantified in calories or is quantified in calories. Materials with lower specific heat capacity than water, they heat up or cool down more rapidly. That's why there are experiments that we can do. There's an experiment that I believe you guys are going to do in this course where you are going to use a calorimeter and you're going to place hot water or water, not hot, and you're going to heat it up with a piece of metal, right? And then you're going to transfer that metal to a glass of cold water. And you're going to see how they reach the equilibrium. Right? That equilibrium is reached by the two substances. Basically, the thermal equilibrium. And what you notice is that while the steel loses or decreases its temperature quite sharply, water does not increase its temperature that much. That's because of the difference on the specific heat capacities. Here's the question for heat. Q equals to mc delta T, where m is the mass, little c is the specific heat capacity, and delta T is a change in temperature. All right? And here's what I was explaining, right? When two objects at different temperatures are placed in contact, heat will flow from the object that has a higher temperature to the object that has a lower temperature. That's just how nature works, okay? Temperature is a quantity that tells us in which direction the heat will flow. Transfer of heat. And then we can talk about phase changes and latent heat. Latent, by the way, means hidden. Why is that? Because you saw that the question of heat depends on the change on temperature. However, there are situations like latent heat where the increase or the heat, the thermal energy, doesn't depend on the change on temperature, right? It's just a factor of mass and something that we call the latent heat of fusion or latent heat of vaporization. If you are melting water or if you are boiling water, evaporating it, which is the correct term. You can melt ice. You can vaporize water. After you start boiling it, you can vaporize it. When water reaches 100 degrees, that's not vaporizing it. Vaporizing it is when you change all the water in liquid form to gas. So that's basically a phase change or change of state. Solid to liquid, liquid to gas. And also the other way around. You can also, if you are increasing the energy, you are basically melting ice and then evaporating water. But if you are solidifying water, which happens on winter, right? You are absorbing energy, right? So that is a decrease of that absorption of energy is quantified by the decrease of temperature. So let's take a look at this example, right? You have ice with this, the specific heat capacity can be given in joules or calories per gram per Celsius, by the way, right? And in calories per gram per Celsius, you see, these are easy numbers. 0.5 is the specific heat capacity of ice. And it's asking you how much heat you need to raise the temperature from -10 to the melting point, which is 0 degrees. So the change on temperature is just 10 degrees Celsius. The specific heat capacity is 0.5 and the mass is 200. Now everything is in grams, Celsius, calories. So the energy will be in calories, 1,000 calories. All right. So that's basically how you do these problems. I will probably do another video where I go over other problems, but for now, these examples are nothing out of the extraordinary. Now, if you are doing latent heat of fusion, that is when you want to melt the ice. So the mass, remember conservation of mass, all the ice has been raised from -10 to 0 degrees Celsius. And now you're going to melt the ice. To melt the ice, you're going to multiply the mass times the latent heat of fusion. Okay? Which is 200 times 80, 16,000 calories. Nothing difficult, right? And then how much heat do you need to add if you are raising the temperature from -10 to totally melted? You're going to add the 16,000 plus the 1,000. Look how much more energy you need to melt, to do a phase change. Okay? That should give you an indication of the large amount of energy needed to evaporate. And to evaporate water is even more, because the latent heat of vaporization is not 80, it's 540 calories per gram. So way more energy to vaporize water than to melt it, than to melt ice. That was sometimes you use kilocalories, by the way. Instead of writing 17,017 kilocalories. Okay, so Joule's experiment, there are different ways of doing the Joule's experiment. You can do it using electric energy, where basically you use a heater and a resistance, and you want to see the equivalent of heat by using electric power, aka electric energy, and heat. However, you can also do it with masses, right? Pulleys, masses. Remember that you have potential energy here, and that potential energy can give you energy to increase the temperature of water. So you can find a relationship between joules and calories. Here it is. All right. And now let's go with the first law of thermodynamics. The first law of thermodynamics, guys, is actually the conservation of energy, right? The energy given to a system, heat, Q, is equal to the internal energy plus the work done by the system or on the system. That work can be positive or negative, right? And why do I say that law of thermodynamics is basically the conservation of energy? Because I'm going to use a whiteboard for this. There. So this is heat. This is work. This is the internal energy, which is the sum of kinetic and potential energies of a system, by the way. And this makes more sense when we start talking about processes like isothermal, and it's in the slides, isothermal, adiabatic, isovolumetric, or isochoric, right? Isobaric as well. The isobaric is at constant pressure. The isothermal is at constant temperature. And the adiabatic is when the heat is zero. So no energy emitted or released. There are, like in a further course of thermodynamics, we go over that with the students because there are different types of thermal machines that we can create, like refrigerators or thermal machines, like you're going to see in the next chapter, where we can use these different processes, right? For the isobaric, for example, if the pressure is constant, the work depends only on the value of the pressure and a change on volume. So you can easily find the work. For isothermal, it's a bit more complicated because you have like a curve. Okay. Now, the most common application for thermodynamics are pistons, where you have like a cylindrical piston. Sorry. You have a cylindrical piston and you can exert some work. You can either expand the gas or compress it by an external force. And what's force times distance? That's work. So if the work is done by the gas expanding, the work is positive. If you're doing it on the gas, the work is negative. Okay? So heat measured in joules, work measured in joules, internal energy measured in joules. You can also measure them in calories. You can also measure them in calories. And sometimes it is better, as you saw in the previous examples, to measure them in calories. Okay? So for example, look at this, right? A hot plate is used to transfer 400 calories of heat to a beaker containing ice and water. 500 kilograms of work are also done on the contents. So if you're doing on the contents, the work is negative, yeah. What's the increase in the internal energy? So you multiply 400 calories times 4.19 to get the heat in joules. And then the change of internal energy is the heat minus the work. But hey, minus the work is 2,180 joules. All right? That's the change of internal energy. Now, that's the energy given to the ice. You can also find how much of that ice was melted. It's here. How much ice melts. So that energy is equal to the mass of ice melted times the latent heat of fusion. Now, the latent heat of fusion is 80 calories, so you have to change this to calories. So you divide this by, you divide this by 335 joules per gram, and that gives you the amount of grams, right? You can change the latent heat of fusion from calories to joules per gram, here. If it was per kilogram, it would be even more than that. Because 1,000 grams is 1 kilogram. Okay? Here's what I was talking about, the piston. All right. If the gas is being compressed, the change in volume is negative, the work is negative. That makes sense. You are compressing the gas. Work done by the gas is negative. Negative work done by the gas increases the energy of the system. Yeah, that's the internal energy of the system. Because if the work is negative, that will add to the heat, and that will increase internal energy. If the gas is expanding, positive work is done by the gas, the internal energy decreases. Here's what I was talking about, the different processes, adiabatic, isothermal. For this one, I would just recommend you guys to read what's an isothermal process, what happens with the change of internal energy. For isobaric, what happens with internal energy. All right. And then the ideal gas law is something that we talk about in both physics and chemistry. You probably don't see it like this. This is an alternate way. This is with a number of molecules. The way you probably see it is with PV equals to nRT, right? Like this. Pressure times volume equals to nRT, where N is the number of moles, T is a temperature, R is the constant, the gas constant, sorry. Pressure is pressure, V is volume. So here we're looking at the expansion. Remember we talked about hot air balloons in the previous topic with Boyle's law, right? When you have an isobaric expansion, the gas expands and the density decreases, right? You have more volume, then the density goes down. That will make a hot air balloon rise. And for the flow of heat, just review conduction, convection, and radiation. Conduction is basically contact. Convection is convection currents that can happen during summer nearby the ocean, right? Heat, cold air goes down, heat goes up, and vice versa, goes like that. We normally see convection currents when you are cooking. The hot, right, the bottom of the pot is on the stove, right? It's in contact with the stove. Then that's heating up, that's rising to make sure that everything is warming up. And whatever is cooling goes down, and then you have a process there, like a recycling process, okay? So convection is convection currents. Radiation is how we get energy from the sun, okay? So in conduction, heat flows through a material, right? Normally when you touch something, you have conduction. In convection, that's again, convection currents, there you are. That's how you can heat a house. And in radiation, you're looking at electromagnetic waves. Light is an electromagnetic wave that emits light and energy. Okay? And that's basically what I want to cover for this chapter, guys. There's not much. I mean, some of these concepts you may have seen for the first time. Some you probably have seen before, right? At the end of the day, what I want you guys to learn from this is all the different concepts. And I will do another video with problems where we can go over and we can apply some of these concepts, all right, just like we did with the previous chapter on fluids. So I don't know how long I went for this video, but I hope this is enough to clarify some of the concepts and what you have to pay attention when you are reading the slides. Okay, guys? So have a good day. I'll see you guys on the next video. Take care.